All right, let's just review this a little bit. So on page 350, okay, so biaxial stress is shear and normal stress from two directions, x and y. So we got sigma x, sigma y, tau xy, and tau yx. Tau yx is equal to the negative of tau xy. Those are givens. Those are things you can find using standard design equations. You can find stresses at any angle you want based on the ones above. We call those sigma x1, sigma y1. Tau x1, y1, and tau y1, x1. Okay, so we can find the angled stresses below. Okay, and you use equations 25 and 6 to do that. Okay, there's also that shortcut equation 31 that if you have sigma x1, you can find sigma y1. All right, we can also find what we call the principal stresses, which are the maximum and minimum stresses in the plate. Keep in mind that maximum and minimum really mean kind of most positive and most negative, might be the better way to say that. I tend to think of stresses as absolute values, okay? And you find the angle at which the maximum axial stress acts using equation 27. Tangent 2 theta is tau xy over sigma x minus sigma y over 2. There's two solutions to that are 90 degrees apart. If you go 45 degrees off of those angles, you get to the planes where the shear is maximum. Okay. And then also we've got this kind of these extra relationships here, that tau max is plus or minus sigma 1 minus sigma 2 over 2. On the sigma 1 and 2 planes, tau is 0. So on the principal stress planes, the shear is 0. And on the tau max plane, the normal stress is the average normal stress. So why don't we have a look here at just a couple examples that might serve to illustrate this. I'm on page 370 is what I'm at. And what I'm going to do, I'm just going to show a couple examples of this that involve failure. Now, things don't usually fail. You know, we don't like it when they do normally. But it does help to visualize this a little bit. So that's my intent here, is to just to show you some examples of failure so that you can visualize what we're talking about with this. So what we're going to do, we're going to look at three cases. Three situations with three different materials. And we're going to kind of look at the material and think, well, how would this material fail if it failed? You know, how would it break? All right, and then we're going to look at this biaxial action as far as failing the material. All right, so let's start with sheet metal. If you know, I don't know if you, sheet metal is like a real thin, sometimes it's kind of galvanized metal. There's different kinds of sheet metal. What's sheet metal weakest in? Tension, compression, or shear, do you suppose? If sheet metal is going to fail and not do the job you want it to do, what's the mode it's most likely to fail in? Yeah, compression, because what happens when you push in on sheet metal? Bows out, yeah, it folds. It buckles is the term for it. All right, so really what I'm looking for there is a compressive failure. That's how I would expect sheet metal is going to fail. So what I did there was I ran the numbers for you on a given case. So what I've got is if I'm going to put sheet metal under these loads, these stresses in the x and y directions, I went ahead and I calculated sigma 1, which is or theta 1, I'm sorry, that's one of the principal angles. At that angle, I've got a normal stress of negative 20,707. That's the principal stress. The other principal stress is 9707, and the maximum shear stress is 15207, with an average normal stress of negative 5500. Okay. So let's say I apply these loads to some sheet metal and they cause sheet metal to fail. What angle is it going to fail at? If I just start pushing in, and let's just say I take these loads and I just proportionally just keep increasing them until I hit the failure load, and let's say the failure load occurs in this loading situation, it's going to fail in compression. So what angle do you think it's going to fail at? Okay. Where's the compression going to be greatest at? Because that's where it's going to fail. Okay. All right, so what's going on here is we've calculated up the principal angles, okay, where the stresses are maximum. That's what principal stresses are, okay? Here they are. We've got one principal stress is negative 20,207, and the other one is 9707. So I've called these principal stresses maximum and minimum, but really they're the most negative and most positive. That's the biggest negative stress right there. That's the biggest compressive stress that this plate is going to feel. And it's occurring at 40.3 degrees, okay? So what I would expect to happen to this sheet metal is at 40.3 degrees, like that, I would expect there to be the largest compressive stress acting in normal to that plane. Okay. So in a practical sense, if that were to occur, I would expect that sheet metal to kind of accordion in at that angle. Okay? That's the failure I'd expect. That's why we're doing this. That's what we're talking about here. These equations allow us to take x and y stresses and from them predict where the biggest stresses are, what they are, and how they act. Okay, so I would expect that sheet metal to crush in at 40.3 degrees, and that there to be a normal stress like that, and they would kind of accordion in. That's what I would expect would happen. So I would start with something like that, and it would crush in like that. So I would find the 40.3 degree angle, and the stress is normal to that. So that thing would crush in normal to that 40.3 degree angle. Y'all okay with that? Okay. So that's the meaning of these numbers we're running. That's why we're running them. And that's kind of the meaning of them, all right? Y'all okay with that? Good. Okay. How about concrete? What's concrete weak in? It's got a, yeah, tension. It's pretty famous for that. Concrete does not handle tension very well. It's a bunch of little grains. There's no lap between them. It's sand. It's kind of glued together basically with a line kind of glue. There's no lap between the grains, so you don't get a tensile strength. So yeah, concrete's weak in tension, see? So what I've got there is the angle and the loads. So if we put a concrete plate, not that I've ever seen a concrete plate before, but I guess maybe I've seen something like it, but there we go. So if I put it under that pattern of stress and it's going to fail, I'm going to expect it to fail where the tension is the greatest, okay? All right, so what I've got here is an angle, negative 32.5, and I've got the greatest tensile stress right there, okay? So what I've got there is a negative angle, which means clockwise. So what I think is it might be easier to draw that over here. Like that. And that's 32.5. It's clockwise, so it's probably easier to draw it there. And I'm going to have a tensile load that causes failure there. So if that concrete plate were to fail, it'd do something like that. Okay, it would split apart, would be my expectation. Okay, so a corner would break off essentially. So that's what I would expect. And again, these equations allow you to predict what's going to happen. So at that angle, I would expect to have a tensile failure. Okay? So just pull apart like that. Okay, that's the idea. Okay. All right with that? Okay. So something like that. So we got that 32.5 degree angle. It's negative, so it's clockwise. Tensile load would just pull that thing apart. Boom. Okay. How about soil or sand? Now there's different weaknesses with this. I don't know if I have the right one up there or not, but maybe I do. I hope so. All right, so what's the, whoops, I guess I got it up there. Soil's pretty famous for shear failure. So what's a shear failure? If you're on a slope of soil, you got a shear failure. What do you call that? Landslide, yeah. You got one plane sliding across the other, okay. That happens with snow too, right? If you get, especially around here, you get a snowfall, it melts, then it freezes, you get kind of a glazed surface on the snow. The next snowfall will slide right across that, right? Shear failure, okay? Okay, now here I got 15.5, right? So that's my angle. That's my principal angle. So what angle will the shear occur at? What do you got to do to get the shear angle? It'll be 15.5, and then what do I do? Add 45 to it. Remember that? Okay, so that'll get me 60.5. Okay, so that's the angle where I'd expect that shear failure to fall. To fall. Now I don't know if I got the right stresses on your handout or not. I can't remember if I updated that. It should be negative 8,000 in the X and negative 3,000 in the Y. I don't know. You might have to doctor yours to make it look like that. I don't know. The thing with soil is it's normally under compression. You know, soil loads are compressive. So we're going to have a shear failure at 60.5 degrees. Now tau max there is 2915 is what I've got. All right, so that's going to be occurring 45 degrees off of that 15.5 degree plane. So I'm going to have a shear like as I'm showing there. Okay. And okay, so right at 60.5 degrees, what I've got is a positive shear failure. So what I've got then, positive shear on this side would be counterclockwise. Positive shear on the other would also be counterclockwise. So I get kind of that differential shearing action. On one side it's going up left, on the other it's down right. And that is positive, right? Yeah, I've got this mislabeled, don't I, on my sketch? Or actually not, no, because I've got them, okay, I've got them going the right way. So what's going to happen here is the, or do I? Let's see, that's counterclockwise, that's counterclockwise. Okay, yeah, I do. So what's going to happen then is that one side will slide with respect to the other in that direction that I'm showing. Okay, so the top piece will slide to the right and the bottom one will slide basically to the left there, okay, because they're both under counterclockwise shearing. I'm sorry, I got that turned around. I'm sorry, I've got that a little bit mixed up. I might need to revise that because I've got the thing landsliding uphill, which isn't really good, but I might have to fix that. Okay, so what I've got there is, based on the calculations that I had there, I've got tau max is 2915. It's positive, so that's going to apply the shear stresses that I'm showing there on the different sides. I'm showing them kind of like a couple up here, so to speak. So I get the left-hand triangle going up left, the right-hand shape going down right. And I'm going to have to revise that for next year, I think, because what I've got is, again, I got the thing landsliding uphill, which doesn't make a lot of sense. But, oh well, we'll have to run that one again sometime, okay? So y'all okay with that? That's just, I'm just trying to visually get it across why we're doing this. Sometimes we do so many calculations on this that it's just a bunch of numbers. And this is why we're doing it. So we can predict if something will fail, and if it does, where and how. That's what we want to know, okay, when we're designing things. Okay. All right. So let's look at a couple other examples and have you do a couple of these. Let's say we've got a wooden board and its stress is shown, and I don't think I've got this in your packet, I don't think. Okay, so we got a wooden board, stress is shown. Find the normal stress and the shear stress on plane AB. Plane AB runs along the grain of the board. So we've got these stresses applied to this board. We've got the grain running as shown at 65 degrees. Let's find the normal stress on the shear stress on plane AB. And if the normal stress were to cause the board to fail, what would the board look like after it failed? Okay. So just like you do, I'd want to fill in that table there. Okay. That'd be step one. And then get the right equation and plug the stuff in and see what you get out of it. The one thing I'd caution you on is be sure you're using the proper angle when you do this. And I think I've used this example before, but yeah, this is a good example of why you might do this, you know, because you know on this example that there's a grain running through the wood. It's a weak plane. You know, that's a plane especially susceptible to shear type failure along the grain. So you might want to have a look at that and say, okay, what's the stresses on the grain of the wood? Okay. And we've got the equations that kind of combine the effects of the X and Y stresses to help us find that out. So what's the shear, or the sign on the shear there? That's positive, yeah, okay. And again, if you ever have any doubts about that, just put your book up against the wall and push on it this way and see what it does, and it'll rotate counterclockwise. And just like the moment sign conventions, that's positive. Okay. How about the angle? What's that going to be? Spoiler alert, it's not 65. What's it going to be? 25, yeah. Okay, so just watch that, okay? Because see, out in the field, people might measure things any which way, but the equations are based on from the vertical plane counterclockwise. And there's nothing magic about that. It's just somebody at some point decided to use that. You know, there's nothing, you know, fundamental about that. It's just, that's just how they derive the equations. Okay. And then once you got that stuff, it's just a matter of plugging stuff in. I mean, that's about it after that. It's just important on that, what up above, that when you get the proper signs on things, especially to shear, pay attention to that. And then the other thing is get the proper angles in there too. Okay. And the angles measured from the vertical plane counterclockwise is positive. And remember to use 2 theta for the angle too. Double up the theta, shifting out 25. About 2.56 for that normal. All right. Okay. Shear, I'm getting about -0.33, something like that. Is that all right? All right, so they're 2.56, we're good? Okay. And -0.327 is what I got. So we're good with that. Okay. All right. Why don't we look at one other. Okay. Just sketch those up. What do they look like on that plane? And what's this thing? If this thing breaks, what's it going to look like? If that wood grain can't hold that, what will the appearance be? So got some idea on that? Okay. So if this thing were to fail, what we've got kind of a tensile stress there, right? I'm going to pull them apart. We also got a negative shear stress. So what would happen there? Something like that on the planes. So I just drew them right on the planes. Tensile pulls apart. Negative shear stress is clockwise. I think they look like couples to me, if you remember that from statics. I mean, they're not really couples, but it's kind of what they look like. So that's how I think about them. So kind of a clockwise couple. So if that thing's going to break on that plane, if this were enough stress to make that happen, it's going to what? Pull apart, and that top or the right-handed piece is going to move down a little bit. The left-handed piece will go up a little bit. That's how I would expect that to break if it were to break. Okay, you okay with that? Okay. So something like that pulls apart on that plane. Plus the one on the right goes down a little bit. The one on the left goes up a little bit on account of that shear. Okay. And the thing is too, when you're in school, you calculate everything, and you do an awful lot of it, and that's kind of the challenge. But when you're working, the challenge kind of shifts a little bit. When you're doing design work, it's not you can run the numbers when you're doing design work. You can, if you don't know how, you can ask people and figure it out. But the important thing is going to be to know what you got to be thinking about. Like if I got a piece of wood, and I'm going to apply those loads, I got to go, well, what's going to happen to it? What do I got to worry about it when I design it? And one thing I'm going to worry about with wood is the grain. You have to kind of put together, okay, I got to do some biaxial here. I got to look at that stress on the grain, and I got to have some idea how it would fail. That's kind of what happens. That's one of the shifts that happens when you start working. You focus more on the assumptions. In school, you're given the assumptions. It's this and that in the book. But at work, you got to start figuring out what your assumptions are. It changes. Okay. You okay with that? Okay. Let's see here. We just at least write this thing down here. So what we've got a ceramic plate this time. Now ceramic is kind of like a plate, like a dinner plate. You know, it's like concrete. It's got grains that have been glued together basically with some heat treatment, I guess, for ceramics. It's weak in tension, all right? So why don't we at least get this thing written down? We'll have a look at it on Friday, I think. But this is just another way to review what we've been doing. And what we're going to want to do here is let's say we've got these plates and they're failing. What's the best way to reinforce them? If we're going to, when we make these things, if we're going to put some light steel rod in there, how should we run the rod? Okay, you know, should we run it horizontal? Should we run it vertical? Should we run it at an angle? What would we do? Okay, that's what I'm asking on this problem. And we could have a look at that on Friday. I'm just trying to get this biaxial idea across to you, not just crunching the numbers, but kind of what it means and why we do it. Okay, why it matters. I remember reading an article once with a boat hull that was having these failures that were happening, and they did some investigations, and there were some weird stresses at one particular point that were kind of tearing it apart, and it was a biaxial thing they had to work through to get to it, you know. All right. But I tell you what, why don't we take a look at this on Friday? I guess it'll be so. And there's no homework due. So now remember that those 4 problems are due Friday. If you want to be studying over the weekend, maybe think about making a copy of them before you turn them in. Okay. Because I'll get them back to you Monday. But you know the test is Wednesday, so kind of keep that in mind. All right. All right. So there you go.